you know. Whenever you walk into a room, maybe it's your bedroom, maybe it's the kitchen, and it is pitch dark. You can't see your hand in front of your face. You reach out. You fumble for that little plastic switch on the wall, and you give it a click. And bam, instantaneously, the whole room is flooded with light. The bulb up there on the ceiling, maybe 10 feet away, maybe 20 feet away, it glows. And you don't even think about it. You just accept it. We say, I turned on the electricity. But what is it? What actually happened in that split second? Most people, even grown-ups, even some teachers, they have this picture in their heads that electricity is like water. They call it juice, right? They think there's a big tank of electrical water at the power company, and there's a pipe. What? Which is the wire? And when you open the valve, that's the switch. The water rushes from the switch all the way to the light bulb, fills it up, and makes it glow. They imagine these little particles, these electrons, zooming down the wire like race cars, starting at the switch and sprinting to the bulb at the speed of light. But I have to tell you, that is completely wrong. It is the biggest misconception everyone has. It is a trick of the mind. If electricity worked like that, if those electrons actually had to run from the switch to the bulb for the light to turn on, you would flip the switch and you'd have to wait. You'd be standing there in the dark for quite a long time. You'd flip the switch, go make a sandwich, come back, and maybe the light would turn on. You see, inside that copper wire, it's not an empty pipe. It is crowded. It is absolutely packed with copper atoms. It's like a crowded dance floor on a Saturday night where everyone is shoulder to shoulder, packed in tight. The electrons are there, yes, but they can't just zoom. They are bumping into things, wiggling, jiggling, bouncing off the copper atoms. It's a mess in there. If you could actually watch a single electron, let's call him Freddie, and you wanted to see how fast Freddie moves down the wire when the light is on, you would be very disappointed. He moves slower than a snail. Literally. He moves slower than ketchup coming out of a bottle. If you have a DC circuit, like a battery in a flashlight, Freddie the electron might take an hour just to move a few meters. He is taking 2 steps forward, 1 step back, bumping into a copper atom, spinning around, going sideways. It is a drunkard's walk. And if it's AC current, like in the wall of your house, Freddie doesn't really go anywhere. He just jiggles back and forth, vibrating in place, never actually leaving his spot. He never actually makes the trip to the light bulb. So if the electrons are moving so slowly, or just wiggling in place, how on earth does the light turn on instantly? Here is the trick. Here is the beautiful thing about nature. Imagine you have a very long cardboard tube, like a wrapping paper tube. But let's say it's 10 miles long, and this tube is completely filled with marbles, packed tight, end to end. Now, you stand at one end of the tube, and you hold one extra marble. That's your electron. You push that marble into the tube. What happens? Does your marble have to roll all the way down the 10 miles to the other end for something to happen? No. You push one in here, and instantaneously, a marble pops out the other side 10 miles away. Your marble didn't travel. It only moved an inch. But the push, the energy, the signal, traveled through the whole line instantly. That is what electricity is. It is not the movement of the stuff. It is the movement of the push. When you flip that switch, you are creating a field, an electric field. You are sending a wave of tension through that sea of electrons. It's like a command that goes out to all the soldiers at once. The switch says, move, and everywhere all along the wire, all the electrons start to jiggle at the exact same time. The electron next to the switch pushes his neighbor, who pushes his neighbor. And this wave of pushing travels at almost the speed of light. So the electron in the light bulb starts moving instantly, not because Freddie ran all the way from the switch, because the news that he should move arrived there instantly. Think of a bicycle chain. This is the best way to think about the alternating current. The AC, that comes out of your wall. You have the pedals, and you have the back wheel, and they are connected by a chain loop. When you pedal, does the link of the chain that is on the pedal have to travel all the way to the back wheel before the wheel turns? Of course not. The whole chain moves as one solid unit. If you wiggle the pedal back and forth just a few inches, the back wheel wiggles back and forth instantly. The chain links aren't really going anywhere. They are just rocking back and forth. But the energy goes from your legs to the wheel perfectly. The electrons in your house, wires are the bicycle chain. The power company grabs one end of the chain and wiggles it, and your toaster grabs the other end and shakes. The electrons just transmit the shake. And here is something even stranger, something that really bothers people when they first hear it. The energy, the actual power that lights the bulb. It doesn't even flow inside the wire. It flows outside the wire. I know, that sounds crazy. You think the wire is carrying the power like a hose carries water. But the wire is just the guide. The wire creates the trap for the fields. When you turn on the current, you create a magnetic field and an electric field around the wire, a sort of invisible halo. And the energy flows through that halo, through the space, and dives into the light bulb. The wire is just the railroad track. The energy is the train running on top of it. The electrons inside are just dancing to set up the fields, so the energy can glide along the outside. It's a marvelous, mysterious thing. Now, let's dig a little deeper into what happens when that energy dives into the bulb. Why does it get hot? Why does it glow? If Freddie the electron is just wiggling, how does that make light? Well, imagine you are trying to run through a very crowded room, a room full of furniture and people. You try to run, but you bang into a chair. Then you stumble into a table, then you bump into a person. Every time you bump into something, you shake it up. You give it some of your energy. Inside the filament of a light bulb, the wire is made of tungsten. And tungsten is like an obstacle course. It's very hard for the electrons to push through. We call this resistance. It resists the flow. So the field pushes the electrons, saying, move, move. And the electrons try to move, but either a whim, they smash into a tungsten atom. They get bounced back. They try again. Whum. Every time they crash, they make the tungsten atom jiggle. And if you get billions of electrons crashing into billions of atoms, the whole wire starts to vibrate like crazy. And what is vibration on the atomic scale? It's heat. The wire gets hot. It gets so hot, the atoms are shaking so violently that they start to shed energy just to calm down. They send out little packets of light, photons. That's the glow. The light is just the dying scream of the atoms being beaten up by the electrons trying to push through the crowd. And this force, this electrical force, it isn't just in wires. It is everything. It holds you together. You are sitting on a chair right now, right? Why don't you fall through it? The chair is mostly empty space. The atoms are tiny, and the space between them is huge. You are mostly empty space too. Why don't you just pass right through like a ghost? It's electricity! The electrons in the seat of your pants are negatively charged. The electrons in the surface of the chair are negatively charged. And what do like charges do? They repel. They hate each other. They push back. That feeling of solidness, the feeling of your butt on the chair, that is actually the electrical force of billions of atoms pushing back against you. You are hovering on a cushion of electric force. You never actually touch anything. You are just floating on fields of repulsion. And this force is incredibly strong. We don't realize how strong because everything is usually balanced. For every negative electron, there is a positive proton neutralizing it. It's a perfect wash. But imagine for a second if we messed up that balance. Just a tiny bit. Imagine you are standing next to your best friend, arm's length away. And imagine I could magically take just 1%, just 1% of the electrons out of your friend, and just 1% of the electrons out of you. So now you are both slightly positive. Do you know what would happen? Would you just feel a little tingle? No. The force of repulsion would be enough to lift the Empire State Building. Actually, it would be enough to lift the entire Earth. That is how powerful electricity is. It is this sleeping giant, this monster force that is usually perfectly balanced, hiding in plain sight, holding your atoms together, holding the chair together, holding the world together. This brings us to another funny idea people have about batteries. They think a battery is like a box of electricity, like a canteen full of water. You buy it, you pour the electrons out into your toy car. And when the battery is empty, it means all the electrons are gone. They fell out. But that's not true at all. A battery doesn't supply electrons. The electrons are already in the wire of your toy car. They are part of the metal. The battery is just a pump. That's all it is. It takes the electrons that are already there and pushes them around in a circle. When a battery dies, it doesn't mean it's empty of electrons. It means the pump is broken. The chemical reaction that was doing the pushing has run out of steam. The electrons are still there, sitting in the wire. But nobody is pushing them anymore. It's like a bicycle with a dead rider. The chain is still there. The wheels are still there. But nothing is moving. And you know, this explains why you always need two wires. Have you ever noticed that? You can't just plug one wire into a lamp and expect it to work. You need a plug with two prongs. Why? Because the electrons can't just pile up in the lamp. If they did, the lamp would get incredibly negatively charged and explode with sparks. You need a way for them to go home. You need a full circle. One wire is the road out, and the other wire is the road back. It's a circulation system. If you cut the return wire, the whole thing stops. It's like a traffic jam where the bridge is out ahead. Nobody moves, even the people miles back. The circuit must be closed, or the field cannot exist to push them. This electrical business isn't just about wires and batteries either. It's you. It's me. It's how you are thinking right now. Your brain is a thunderstorm of electricity. every thought you have, every itch you feel on your nose, every time you wiggle your big toe, that is an electrical signal zipping down a nerve. Your nerves are just wet wires. They are tubes of salt water, basically with ions, charged atoms, moving in and out of the membrane. When you touch a hot stove, a signal races up your arm to your brain saying, hot. Move. That is electricity. We are electrical machines living in an electrical universe. If you stop the electricity in your body, you wouldn't just be paralyzed, you would fall apart into dust, because the chemical bonds holding your molecules together are electrical too. And sometimes nature likes to show off this power in a big way. Think about lightning. That is the ultimate rubber band snap. Up in the clouds, the wind and the ice crystals are rubbing against each other, scrubbing off electrons, separating the charges. The bottom of the cloud gets negative. The ground gets positive. The tension builds and builds. The air, which is usually a good insulator, tries to hold it back. It says, no passing. But eventually, the tension gets too high. The voltage gets to millions of volts, and the air just breaks. It rips apart. The electrons smash through, creating a channel of plasma, and crack, the lightning bolt. That is just the universe trying to get back to balance, trying to neutralize that 1% difference I told you about earlier. So when we generate electricity, we aren't creating new stuff. We aren't cooking up electrons. We are just separating them a little bit. We are taking this balanced soup and pulling the positives here and the negatives there, creating tension. We are like stretching a rubber band. The wall socket in your house, it's just a place where the rubber band is stretched, waiting to snap back. When you plug in a toaster, you are letting the rubber band snap back through the toaster wires. And as those electrons rush to get back to balance, they crash into the atoms in the toaster wire. They bang around. They create friction. And that friction makes heat. That's why your toast gets brown. It's the friction of the electrons trying to get comfortable again. It is a marvelous thing, really. We use it every day to run our TVs and our computers and our lights, and we think of it as this simple utility. But it's really the main rule of the game for matter. It's the force that makes chemistry work. It's the force that makes fire burn. Did you know that? Fire is electricity. When a log burns, it's the carbon atoms snapping together with oxygen atoms, and that snapping together releases energy in the form of light and heat. It's all the same thing. It's all just the jiggling and snapping and pushing of these tiny charged particles. So the next time you flip a switch, don't imagine a little drop of water running down a pipe. Imagine a vast, invisible ocean of particles, billions and billions of them, sitting there in the dark, waiting. And when you click that switch, you send a shock wave, a command, a field that screams, "Wake up." And the whole ocean dances at once. That is the magic. It's not the travel, it's the connection. It's the fact that everything is connected by these fields, so that a little wiggle here can cause a massive glow over there without anything having to make the long journey in between. That is the real fun of it.